Hi, I'm Gabriel from Germany, from the University of Deggendorf, and I want to talk about the CT data completeness conditions for sets of arbitrary projections. I'm researching twin robotic CT systems for industrial CT. In this case, we have two robots. The source is mounted on one of the robots and the detector is mounted on the other robot. And now they can move around big objects, in this example, a bike. And now they can scan different parts. They can do very flexible movements. So yeah, it's super cool and in theory powerful, but there are a lot of challenges. So the result of this scan was a 2D stitched X-ray image of a bike. So you can make really big X-ray images, but of course we do not want to stay at 2D. We want to do 3D, but 3D is can be really complicated. So the problem is in complex use cases. For example, here I simulated a motorcycle. The question is, which trajectory do you want to choose? Which directions do you want to choose? It often depends on which directions you can, which direction you can scan. And then some directions are better because of less attenuation, because of the metal or anything. In this example, the green dots are the possible source directions. And from these green dots, you should choose some of the directions and then use iterative reconstruction. And now I want to know in this talk, what trajectories or what sets of views provide sufficient data for complete 3D reconstruction. And yeah, the motivation, normally there's a two-step approach applied. First, normally you choose a continuous curve, most of the time a circle or a part of a circle or maybe a helix. And then you choose a sampling strategy based on the Nyquist-Shannon sampling theorem. Most of the time, equidistant points of this curve. And if it's done correctly, then we know it's data complete for this application. But with RoboCT, there's a lot more possible. The question is, what do we do for arbitrary X-ray views? What do we do if we have something like these things like strange sampling on a half circle or a complete the other thing, or how can I do this? So this was application specific, for example, using an optimization process. This is like random sampling, or this is for the motorcycle. So I want to quantify how good are these sets of views. Are they data complete or not? And yeah, I need to go in the detail in the state of the art. For the curve, normally we use the Dewey-Smith condition. Intuitively, it means that if all planes through the volume intersect the source path, the volume can be reconstructed. What does it mean? Here I have a sketch, the source, and here the detector. And with each view, we measure these lines, these line integrals, which correspond to planes. These are the planes that are mentioned in the Dewey condition. And each of these planes corresponds to a normal vector. And with each view, we generate a circle of normal vectors. And now if we rotate the thing, for example, for the circular trajectory, this circle rotates too. And we have measured all of these planes. We have measured all of these normal vectors, and then it's fine. Intuitively, it means that for every possible surface, these planes, there has to be a parallel X-ray, then it can be reconstructed. So that's the Dewey-Smith condition in short. Problem is that Dewey made some assumptions. And first of all, he assumed a detector with infinitely small detector pixels, which is impossible. And secondly, he assumed a projection at every position on the continuous trajectory, which means an infinite number of projections. That's impossible too. So we need a sampling strategy for the pixel size, spatial sampling, and a sample strategy for the angular sampling. Normally, it's a number of projections. So we need, if that's a detector, we need the distance of this measuring points, and then we need the angle of different projections. Yep. The sampling is based on the Nyquist-Shannon sampling theorem. The frequency of the sampling needs to be at least twice the size of the signal frequency. And yeah, important parameters are the size of the minimal relevant object feature, F-min, the magnification factor due to the cone beam angle, K, and the radius of the measuring field, R. And then following Nyquist, we get these two equations. I do not have the time to go more into detail. For example, here's the source. The spatial sampling, the size of the pixel needs to be smaller than K/2 times the size of the minimal relevant object feature. And for the angular sampling, it needs to be smaller than 1/2R times the size of the minimal relevant object feature. So that's, yeah, good. To recapitulate, normally we choose first TUI, a continuous curve, then the sampling, but this cannot be applied here as we do not have a continuous curve in the first place. So the idea was to just combine TUI and Nyquist in one step, in one condition, so that it can be applied even for this strange stuff. So first of all TUI plus the angular sampling. I have the sketch again, and I call a normal vector U, and an X-ray corresponds to the normed directional vector of this X-ray from the source position L to region of interest. And the TUI Smith condition says that for every point in the volume X and for every direction, there needs to be a source position so that we have an X-ray that's perpendicular to this direction. However, that's impossible because then we would need infinite X-rays. So the TUI Smith condition combined with this angular sampling of Nyquist means that for every point in the volume and every direction, we need to have a source position so that it's almost perpendicular. So the sign of this product needs to be smaller than the angular sampling rate, and that means that for every possible direction U, there has to be an almost perpendicular X-ray, except of this angular sampling. And analogs, this means for every possible surface, there has to be an almost parallel X-ray, depending on this angular sampling rate. And now if I additionally introduce the pixel size that I mentioned earlier, we get one condition, one data completeness condition for sets of arbitrary projections. So it doesn't have to include any continuous trajectory or anything. An object in region omega can be reconstructed based on projections with corresponding source position L if the maximal pixel size is small enough, depending on the smallest magnification factor K and the smallest relevant feature. And if for all points in the volume and all directions, there exists a projection with corresponding source location L, so that we have an X-ray that's almost perpendicular to every direction. Yes, depending on the angular sampling rate. It's an easily verifiable condition for every set of projections. So let's try. First of all, I start with something very simple. I want to show a circular trajectory. But first, the red dot corresponds to the current source position. The blue dot here is the region of interest. Here it's in the center. And this X-ray, with this X-ray, we measure planes which normal vectors are perpendicular to this direction. So if we get this circle visualized by the normal vectors. So if we start rotating to get a circular trajectory, these normal vectors are measured, these planes are measured. And if we add all of these directions up, all of these normal vectors up, we can see that we have measured all planes. Therefore, data complete for this region of interest in the central plane. However, if I move the region of interest to the bottom, then this X-ray is tilted, and analogically, the circle is tilted. And if we now rotate, we see that this tilted circle is rotated, and that therefore, yeah, directions are missing, and that's the reason for cone beam artifacts. An easy example, and yeah, to continue this easy example, I simulated a very basic round object, a round sphere with these layers, and yeah, with a circular trajectory. And we can easily see in the middle it's fine, and at the top there are artifacts as expected. But I want to quantify it. So here are the numbers. The radius of this object is 1 centimeter. I set the smallest relevant feature to 0.03 centimeters. That's the size of one of these layers. And then I calculated the angular sampling rate. That's 0.015 radian. And now I calculated the real angular sampling rates at the center and at the bottom. And we see in the center, the sampling rate is 0.013 radians. That's fine. Therefore, we do not have any artifacts. And at the bottom, it's way too high. We have 0.308 radian. And yeah, that corresponds to those artifacts. So in this case, I calculated this sampling rates at 2 points. And of course, we can do it at more points. Therefore, I calculated data completeness maps. In this case, for 2 half circles with plus opening angle. And these data completeness maps correspond to the central plane. And in this first case, we see that in the plane of the circle, data completeness is perfect. But if we go in the y direction, data completeness gets worse. Again, cone beam angle. And again, as we expect, if we rotate the half circle, this data completeness map rotates too. So that are the easy examples. So what happens if we go a little bit more complicated? In this case, I fused both half circles, and then I get this thing which here has perfect data completeness. Note that the scale here is different. So here it's still better than here. But with 2 half circles, we have perfect data completeness here, which is to be expected. And here in this case, I sampled randomly on a half sphere. And now we get like this sampling, which is quite fine, but depending on the use case, might still not be enough. But we are able to quantify the data completeness even for random sampling. And now wanted to show a more complicated use case. In this case, I have a plastic object surrounded by metal plates. And in this case, the metal was so dense that the information of the X-rays that had to pass this metal would lead to artifacts, or there was just no information. Therefore, I ignored this strongly attenuated X-rays. And in this case, I used, again, a circle. In this case, I wanted to check a trajectory that I have optimized. So it's a circle that's a little bit, that's not in the center, with an appendix and some kind of random projections, but that's what my 3D optimization resulted. And now I wanted to check what's the data completeness. And here's the results, the data completeness maps and the reconstructions. And first of all, we can see that in both cases, near the metal, there just is no information if I do not regard this X-rays. However, due to the geometry and that I disregarded the strongly attenuated X-rays, there are a lot of regions where there's not enough information. And we can see that here. The reconstruction using SART is very bad. But in this case, with other views, with optimized views, you can see that there's almost ideal data completeness. And we can see that in the reconstruction results too. Yeah, it's a little bit noisy, but that's it. Yeah. So with this condition, I'm able to quantify data completeness, can check whether or not there's enough data completeness in a region, and I can quantify heuristically for each data point whether or not I can expect artifacts due to yeah, incomplete data. That's it. More example, more quantitative evaluation and trajectory optimization approaches are in my hopefully soon finished PhD thesis. And yeah, outlook is further testing on real robotic CT systems. Right now, the problem is that the robots are not calibrated well enough. I want to do more complex trajectory optimization, and I want to do it on cool real-world application. Yeah. Thank you. Any questions?
Questions?
I like this, but maybe I missed, does your methodology involves the dimension of the detector system, or it's just source samples?
As I assumed that the detector right now is opposite to the source. I should have mentioned that, but that's not necessary. From my method, it would not be necessary. However, it would be a lot more difficult to visualize it in this 2D images. So in these cases, I assume that the detector is always perpendicular, but the method works even if the detector is different.
And it's like a flat panel.
In this case, it's a flat panel.
And the number of detectors.
But it could be anything.
Okay.
First of all, that's a super cool system.
I agree.
I want to buy one at our institute if possible. More serious question. Great work there. So like right now, if I heard correctly, you have a predefined geometry, then you can calculate the data completeness conditions. And you hinted here, like you want to use this, somehow use this to optimize the trajectory, right? So basically, to say, given this bicycle, how do you optimize the angle? Can you elaborate a little bit? How do you want to do the optimization process? Is there any chance you can calculate, say, incremental like completeness?
I already published another paper or other stuff. The main idea is to exactly increase this data completeness thing. And right now I use the greedy approach. I just checked which projection would add the most data completeness. But obviously you can go a lot more elaborate, a lot more complex.
So just one more quick question on that. So the data completeness, I'm wondering your thoughts about this related to reconstruction algorithms. So if say you do analytical reconstruction, I think that's great, fantastic. Iterative reconstruction, hypothetically, if you use iterative reconstruction, which I think probably more fit to this kind of arbitrary geometry, do you think the data completeness, the relationship between how complete the data is to how good the image quality, do you think their relationship similar as a filter back projection, or is very different?
Yes, I think there's a clear correlation. In my hopefully soon finished PhD thesis, I have a lot of quantifiable stuff, and there is a great correlation. It depends on the other artifacts in the volume, of course, but there is a correlation, yes.
Thank you. Keep that, don't sell to him. I want it. Very interesting work.
Thank you.
I was just wondering, you're doing sort of completeness analysis.
Yes.
I assume it's based on continuous model. You know, there are a lot of talks today talking about sparse sampling.
Sure.
How do you reconcile that? Because you know, there's no way Nyquist condition is satisfied.
Yes, I agree. I assume that Nyquist is necessary. However, if Nyquist is not necessary, then I think you still need some kind of necessary angular sampling, and then you should just could.
Is that going to be object dependent?
I suppose so, but I'm not a sparse reconstruction expert. But that would be a cool combination, of course. Yes.
Thank you.
Thank you too.
Hi, nice talk.
Thank you.
I'm just like more general question about movement precision, or like reproduce, like how accurate is your movement of your and what kind of maybe potential spatial resolution you're hoping to achieve?
Right now, like I said, they're not exact enough. There are other systems that are more precise, but with this KUKA robots, they're not perfectly precise. They're more precise robots. Like right now, I think it's like and the 200 micrometer or any 200, yeah. And we want to be more precise. We want to measure about like, our goal is to go to like 100 or 50 micrometer precision in the volumes. But that's not right. And there are two other colleagues who work on this calibration process with deep learning and other sensors. Yeah, and I hope that will, yeah, thanks.
Let me ask a very simple question. You mentioned R, which is the radius of the measuring field.
Yes.
Can you explain what you mean by measuring field? Is this the radius of a ball that contains the object, or is this the radius of that sphere where your sources are
No,
lying
that's
on?
the radius of a ball which contains the object.
Okay.
The object size, yeah, the angular sampling depends on the object size.
Okay. And so another question related, all the examples you showed, you had the source points on the surface of a sphere.
Sure.
Is that a constraint because of the
That's not
system?
necessary at all. It's just for visualization. I have in one of my publications for I optimized for the motorcycle, and there I have different orbits. But yeah, in 2D, it's difficult to show this stuff if it's not on an orbit, because then nobody understands where in space the points are.
So last question, all these work, I think I caught you just mentioning that your reconstruction method you were using, you always used SART, or did you use an analytic method?
I used SART. Yeah, for this really not circular trajectories, I used SART. And I would like to do more model-based reconstruction, but I just do not have it available. Yes, that's it.
Okay, yeah.
Thank you.
Okay, no more questions. I think we can thank the speaker again and move on.